Welcome to episode 7 of Flat Earth Straw Man. A straw man is an intentionally misrepresented form of an argument which is substituted for the actual argument because it's easier to defeat. Taking this approach is a fallacy called attacking a straw man. I'll be doing the opposite, exposing the straw man to reveal how it differs critically from the real argument, and then providing support for the real argument. Another definition of straw man is a person regarded as having no substance or integrity. So the title of this series serves two purposes, as it highlights how little substance there is to the Flat Earth movement, and the unprincipled charlatans who propagate it with dishonest tactics. Today I'll be looking at a video by one of the upper echelon Flat Earthers, Rob Skiba. This video looks at the Chicago Skyline looming phenomenon, and then attempts to show how refraction can also cause things to appear to dip below the horizon on a flat Earth. His video might not appear to qualify as a straw man, but rather as a bait and switch, but I think I can accurately call it a straw man. First, let's watch the Skyline Skepticism video that inspired Rob's video.
Again, the physics is all the same.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So
Take a moment to observe the setup. The observer's eye is very close to the surface of the table. There is a magnifying glass at the opposite end of the table. There is a picture of the Chicago skyline on the wall beyond the table, and the bottom of the photo is below the surface of the table. This is simulating a globe, where the surface falls away. The distances aren't too clear here, but I approximate the magnifying glass to be about 2 feet from the observer. The lens is about 3 inches in radius, and the picture is at least 4 feet from the end of the table. This is important if you ever wanted to recreate this experiment. Also pay attention to the position of the magnifying glass. This is the most important part.
the atmosphere really is acting like a lens.
Yes. So this is, if anything, this is definitely a demonstration that that refraction displaces the image, and basically where you think the image is not where it actually is.
So you can clearly see that the skyline appears higher up due to refraction. If I go back a few frames to where we can see both the photo itself and the magnified image, frame by frame we can find it. Frame by frame. There we go. So you can clearly see that the skyline appears higher up due to refraction. This upward displacement is due to downward refraction. Because the light is bent downward, it reaches your eye at a steeper angle than if the light were not refracted. Thus, the object appears to be higher than it would actually appear. Now let's watch Rob's video.
Atmosphere really is acting like a lens, and they put a lens in front of the camera to show how it works. So I'm just doing what they're doing.
Notice Rob's claim, "I'm just doing what they're doing." Unfortunately for him, he makes a serious error. Also note that he highlights light as being bent downwards.
I'm using the same logic that they're using, the same science that they're using. And, science is all about testable, observable, and repeatable data, right? So to alleviate the problem of distorting the edges because the magnifying glass ring.
Here Skiba introduces the error. Notice the position of his magnifying glass compared to the magnifying glass from the Skyline Skepticism video. The Skyline Skepticism video placed the magnifying glass so that the bottom half was completely obscured by the table. They were only looking through the top half of the lens, and so they were only getting downward refraction. But here, Rob has placed the magnifying glass higher up. We can see evidence of both upward and downward refraction. For example, the upper right corner of the paper is still visible outside the lens. Yet through the lens, the top of the paper is higher up, which means we're seeing downward refraction. But the edge of the table is lower than it should be through the magnifying glass, which means here we're seeing upward refraction.
Is too small. I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens.
So here Rob completes his error. He uses the entire height of the Fresnel lens, and he places his camera close to the surface of the table, so that he is observing the target through the bottom of the lens. He also places the lens much closer to the target than in the Skyline Skepticism video for good measure. By looking through the bottom half of the lens, he gets refraction in the opposite direction, which causes the skyline to appear to drop below the horizon.
Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is acting like a lens.
You can plainly see that there's downward refraction causing the paper's top to appear higher, and there's upward refraction causing the elements at the bottom of the paper to appear lower. Now let's skip ahead to where he applies the same setup to a sunset, and here he really screws the pooch.
Check this out. All right, here's the first test of a sun moving over a flat surface, and with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward.
Oh, yes, Rob Skiba has called this downward refraction because the sun appears lower. It is, in fact, upward refraction causing the sun to appear lower. I know it can be confusing, but he doesn't seem to be aware of the difference. Now let's go to the coup de grace.
Basically preserved the same size, and the refraction made it set. Now, I'm just going to put forward a crazy idea for you to think about. And that is, if Rob Skiba could figure this out.
Oh, but he didn't. Rob Skiba didn't figure it out. He got refraction absolutely wrong, and that's why he thinks refraction supports a flat Earth. Now, refraction deserves a full video of its own, and I will be doing another video on refraction with a detailed model and experiment. But for now, let me make some general statements about refraction that will suffice to rebut Rob's video. First, downward refraction causes an object to appear higher than it really is, and upward refraction causes an object to appear lower than it really is. This is because the angle at which light enters your eye dictates the direction from which you perceive the source of the light. When the light is refracted downward, that means its angle is steeper than unrefracted light, so the source appears higher. When the light is refracted upwards, that means its angle is shallower than unrefracted light, so the source appears lower. Second, on a flat Earth, where the sun is a constant height above the observer, the sun would never appear to set if there were no refraction, because geometrically, the angle from the observer's eye to the horizon would always be below the angle from the observer's eye to the sun. If there were downward refraction, the sun would never appear to set, because downward refraction causes the angle to appear steeper than it actually is. Third, when Rob Skiba sees the setting sun in his demonstration and calls it downward refraction, he's wrong. If the lens refracted the light downward, the sun would appear higher in the sky than simple perspective alone dictates. Instead, the lens is refracting the light upward, so the sun appears to get lower and lower until the sun can't be seen anymore, because all the rays of light enter the lens and are refracted up away from your eyes. The light that would be refracted into your eyes never reaches the lens. Here are a few simple images from a ray optics simulator. The link will be in the description below. These are highlighting downward versus upward refraction. Here we have a point source, and here we have a lens that is bending the light downwards. What does this mean for the observer? The observer, this blue dot, sees the sun at an angle higher than it actually is. Here's the exact same image, but now the lens has been inverted, so the lens is refracting the light upward. What does this mean for the observer? The observer sees the sun at a lower angle than it actually is. This ray optics simulation here shows how downward refraction cannot cause the appearance of a sunset on a flat Earth when the sun remains a constant height above the observer. First, we will use downward refraction. This green point of light is the sun, and the blue circle here is the observer, and this cone of blue lines represents the direction from which the observer perceives the light to be coming from. So you can see how the angle to the perceived sun is always steeper than the angle to the actual sun. Therefore, on a flat Earth, the sun remains a constant height above the observer, and the light is being refracted down to the observer. The sun will never appear to set. If we change the situation so that we have upward refraction, and I can simulate that by moving this lens like so. Now that we have upward refraction, the angle to the sun, the perceived angle to the sun, is lower than the actual angle to the sun. And given enough distance, the sun would appear to sink into the horizon. This is a lot easier if the sun is much closer to the observer. So, for example, if I bring the sun much lower down, you can see how quickly it appears to be coming from below the ground. Fourth, the conclusion is that Rob needs upward refraction, whether he knows it or not. And that means he needs the atmosphere to increase in density, or at least in refractive index, the higher you go. And that is not the normal state of things on Earth. Occasionally, we get less dense air below more dense air, such as directly over asphalt roads in the sun. But we don't have this density inversion occurring all the time, which would be necessary on a flat Earth so that boats, buildings, mountains, and even the sun and moon would appear to sink below the horizon. We know that the atmosphere gets thinner with altitude and that the refractive index drops with altitude. There are other flaws with this and any flat Earth refraction model, but I think I've demonstrated its primary faults adequately. No point in dragging this video out any longer. Many flat earthers try to use physics to reject the globe model. But as Rob has shown us, he either doesn't understand the physics of optics, or he has to present a false version of it in order to use it. So, next time, flat earthers, if you're going to try to use physics to reject the globe model, use real physics. Don't set up a straw man, because I'll knock it down faster than you can. I'm Night Sky Jeff. Keep looking up.